One of the most important tools in astronomy is the digital camera, which we refer to as a CCD camera. It's a particular type of digital camera. Fortunately, since digital cameras become so common, the language of digital cameras and digital images is quite familiar to us. We're going to talk a little bit about some of that language associated with digital cameras, as well as how these CCD chips, the things inside the digital camera that record the light, how those actually work. So let's take a look at this picture. This is the Ring Nebula. This is actually a picture that I took when I was a student. And let's just look at it a second. What you'll see in the center is this beautiful nebula, and you'll also see then there's stars all over the sky. So this is what a typical astronomical picture looks like, right? Now you see that some of the stars look bigger and some of them look smaller. That's sort of an indication of brightness. The bigger it looks on the picture means there's sort of more light there, right? So it's kind of spread out more. And you'll see that more as we look at more of these kind of pictures. What I want you to notice is that when you've seen this before, but when you zoom in on a digital picture, you start to see a weird thing happen, right? As you get further and further in, you start to see what we often refer to as like pixelization, or you see that these things are broken up into tiny boxes. And you can see all those boxes, right? Like this star that was at the center now looks like it's kind of a square-shaped thing, right? You see all the boxes all around there. And any one of those boxes is actually just an individual color, right? Just a particular shade of red or of blue. But when all those boxes are put together, we get the appearance of this sort of larger structure and stuff that's happening. Well, these pixels are telling us something about how digital cameras work. The camera itself, the CCD chip itself, is broken into millions and millions of these little pixels, right? And that's what we refer to when we talk about like an 8 megapixel camera. We're saying there's 8 million of these little squares. And each of these little squares acts kind of like a little solar panel. That is, it takes light and turns it into electricity. It does that through something called the photoelectric effect. So let me just show you a quick little simulation which illustrates how the photoelectric effect works. So this simulation can be used to show lots of things. I'm using it only in its most basic level to show the idea that light can be turned into electricity. The idea here is that and this is similar to what happens inside each pixel of a CCD camera and inside solar panels in general. But there's a voltage, right? Kind of like you think of two ends of a battery. There's a voltage between sort of two plates. And what happens is that when light hits one of those plates, so I'm going to turn up the intensity of this light, that plate is covered with a material which, at particular wavelengths of light, gives off electrons. And because there's a charge between these two plates, the electrons are sort of forced to move, and it generates a small current, which is what we refer to as electricity. So this is, in a very brief nutshell, what's happening here. Right? The light comes in. For reasons we'll see in a later lesson, that light knocks loose electrons from the atoms in that material. Those electrons are propelled into motion, generating a current, and current can be measured. Right? That's sort of the whole point, is that how are we going to measure light? Well, we're going to actually measure electricity, and that's going to tell us about the light that came in. Unlike film cameras, or film in general, this process is very efficient. Right? So something like 80% to 90% of the photons of light that come in turn into an electron that's produced. Whereas with film, typically only maybe 20 to 30% of the light that even comes in is actually being recorded. So as you can imagine, in astronomy, we want to record every photon of light that we can from deep space. And so a very efficient process, like the photoelectric effect, is very valuable. Now, here's another analogy to help us understand how a CCD chip works. Each of these pixels can be thought of as buckets. And you can think of those buckets as collecting light, but as we've just seen, really what those buckets are collecting is electricity, or electrons, or charge, whatever you want to call that. It actually hints at why it's called a CCD. It's a charge-coupled device, right? It's holding these electrons and it's holding this charge. So the trick, though, is then how can you figure out how much electricity or how many electrons are in every one of those tiny pixels when there's millions and millions of them? And so CCDs use something called a readout process. And this is illustrated with this simulation. So I'm just going to highlight for you, though, that really in a CCD camera, and in fact in all digital cameras, only one pixel is actually read. Out of all the millions, only one pixel is actually set up, the electronics are set up to actually determine how many electrons are in that pixel. So then, well, how can you possibly figure out how many electrons are in all the pixels if you're only measuring one pixel? Well, this illustrates it. So we're going to start this. This is light coming in, right? And it's collecting in these buckets. And you can see that it's measuring what was in this first bucket. Okay, I'm just going to pause it a second right there. What you notice, though, is that what's happening is the charge, or water, is being moved from one bucket to another. It's always reading the same bucket, this bottom right-hand corner, right? But as the charge flows from one bucket to the other, it reads it out, and it puts it in the table. Yeah, so it's just reading down. Now, once a whole row has been filled in, the one row is passed over to the next row, right? So following this process, we can sort of create a map, this sort of table of numbers of how much water was in all the different buckets, or how much light was in all the different pixels, simply by reading a single pixel. This electronics happens very quickly, but this is the readout of a camera. This is why when you take a digital picture, it doesn't show up instantly, but it takes just like a fraction of a second before it shows up. It's getting better and better. This process gets faster and faster. Now, on astronomical cameras, we want lots of pixels, and typically this readout process can last anywhere from 30 seconds to a minute. So you'll take a digital picture, and then you actually won't be able to see it on the computer for several seconds. Okay, so this is the readout process that happens in these digital cameras. What this hints at, though, is how data, what this data really means in a digital picture. And we're going to see this more, but I just want to highlight it for you a second, and that is that every one of these values in this table is a pixel. And that pixel is represented really by a single number, that number being how many electrons were in that particular pixel. Of course, that number of electrons translates directly to how many photons came in. So in other words, how bright is that pixel? If we return to our picture of the nebula, you can see this played out in an interesting way. And this is true, again, of all digital pictures. I'm going to zoom back out a little bit. But if I hover over this picture in different places, and you look in the bottom left-hand corner, you'll see that there's an X and Y location. Right? There's like right here it says 575, 496 pixels. So that's this particular pixel that I'm hovering over. That is telling me what location it has in this giant table of numbers. So this digital picture that we're looking at here is really just a big table of numbers. Right? And this is why when we refer to astronomical data, we're talking about pictures. They're one and the same. We can visualize the data as an image, but really, inherently, this image is just a big table of numbers. There's one more thing I want to show you about astronomical digital pictures, and this idea of pixelization. I'm going to zoom in on some stars here, and I want you to notice something. That these stars, right, up here pixelated, that's normal, that's what we'd expect. But you'll notice that, for example, this star, there's maybe 10 pixels across this star, right? And for a fainter star, I see there's maybe 5 or 6 pixels across it. And for a really faint star here, maybe you can barely see it, there's only 4 pixels across it. And this gets to how telescopes are made. When we made a telescope, we tried to estimate or measure the magnification of that telescope. But you might think, well, with digital pictures, I mean, I can zoom in just like this, right? Like I don't even need to magnify my telescope because I can magnify it on a computer. I can zoom in. That highlights one of the problems with the way we often talk about telescopes. Most times people think, oh, a telescope with a really big magnification is really great, and the more the magnification, the better. But magnification is actually not important at all when it comes to telescopes because I can magnify it on a computer. Magnifying things doesn't actually make it better. What's more important is, and what's really critically important, is resolution, the resolution of a telescope. And that's illustrated with these pixels across here. No matter how much I zoom in with this digital picture, I can't see these stars any better. They're still only 4 or 6 pixels across. I can't see any more details. However, if you can improve the resolution of a telescope, you can make it so that the star maybe has 10 or 12 pixels across. So it's like zooming in, except you're really truly zooming in because you can get higher resolution. The pixels are showing smaller details. The only way that you can improve the resolution of a telescope is by making the aperture larger. So that's why astronomers want really big telescopes. Well, for 2 reasons, right? One is they get more light. So these faint little stars way down here that are really faint look brighter because we're collecting more photons. and we get higher resolution. That is, we can see more pixels across and get to kind of measure subtle variations in brightness across any particular object. Now I'm going to point out that none of these stars are resolved. We aren't seeing any detail on these stars. They're so far away that all we can see is a sort of uniform glow of white. Alright, so there's a little distinction. Magnification is less important. Resolution is really important.